Okay, good. I'm just going to do a very quick overview of Evm Assembler for people who might not be all that familiar with it. It won't make you experts on the subject, but it'll at least get you up to speed for what we're going to be talking about later. And this is a square table because it's not a round table. It's where somebody presents and then people ask questions. This will be me doing a quick overview, and then we all discuss things after that for as long as we need to. Okay, I'm going to share my screen. Hold on a sec. There. Okay, let's get started. I'm going to assume that we all have varying degrees of experience here. Some of us might be very familiar with working at the level of assembly language, and then others will be coming at this as Solidity developers who are curious about the low-level workings of Ethereum. There's also been interest in optimizing Solidity contracts by writing in inline assembly. Hopefully, after this square table, we'll all have a clearer idea of the EVM and its assembly language. Since this is an overview, I'll go really quickly through these slides. If you have any questions, we can discuss them in the part after this. So I will get started. As it says, it's a brief overview, so I'll go pretty quickly. At the lowest level, all CPUs execute machine code. Obviously, a virtual machine doesn't have a physical presence, so its machine code is usually called byte code. Ethereum has a virtual machine at its core that's called the Ethereum virtual machine, oddly enough. The EVM executes the byte code produced when you compile a contract in a high-level language such as Solidity. Because we want it to be easier for developers to write smart contracts, EVM languages go to great lengths to abstract away what goes on behind the scenes. As this is a difficult task, the bytecode produced by, say, the Solidity compiler is somewhat inefficient. As a result, the binaries produced by a compiler are larger than necessary and cost more in gas, both at the deployment stage and when a function on the contract is invoked. One way around this is by writing parts of your contract in assembly. As efficient as it is, nobody actually wants to code directly in hex. One would have to be a bit, loony to do that for any substantial piece of code. Assembly language is a textual representation of the EVM opcodes. Opcodes are the instructions that the EVM executes. Its entire functionality is encapsulated in its opcodes. Writing in assembly language allows you to use these opcodes instead of having to write raw bytecode. It's the most minimal abstraction layer you can put on top of a physical or virtual machine. This is an example of assembly language produced by an EVM language compiler. There are a lot of parentheses in there. One might even say it looks somewhat Lisp-like. But this is definitely EVM assembly language. I'll quickly describe what's going on in this chunk of code. This retrieves a constructor parameter that was, oh no, sorry, wrong. This pre-computes the function ID and stores it in memory for repeated use when trying to figure out what function is being asked for. This is going to be a really quick overview, and I'm not expecting everyone to understand exactly what's going on here, because that's why we're here in the first place, is to figure that out. But so that line just saves the function ID, and it doesn't have to execute the exponent function over and over again just to figure out what function is being asked for. This line checks that function ID to the function ID that was requested from an outside party. So 0x32CAFFED is the function ID of the function that's being called. And what's stored at memory location 20 is the function ID of what was passed in. So if they are not equal, then it jumps to tag 23 at the bottom there, which aborts. That's the equivalent of the fallback function in Solidity. It can be more than just jump tag 0. But if it is successful, it falls through to the next line, which in this case, the function is not payable. So all this does is check that there was no value passed in to the function. So call value holds that value, and if it's 0, it jumps to tag 29, and if it's not 0, which means there is a value, it jumps to tag 0, which aborts. Whoops. There, sorry, I didn't keep up with the highlighting.
I have a quick question.
What's that?
I have a quick question already.
Sure.
In that first line there, you're saying that does that generate a function signature or a function ID you're calling it, or does it just store one?
What it does is when a function is called on a contract, the function and its parameters are encoded in ABI format. So what you get when it comes into a function is a big long hex string. The function ID is in the first 4 bytes. So by doing exponent, that's 2 to the 224th, that will take the first 4 bytes and slide them all the way to the right of the 32-byte number. And that call data load 0 is that. Anyway, so you end up with the 4 bytes of the function ID that was requested and then stored at memory location 20. Okay,
cool. So like exponent 2 really is just, you're just isolating certain bytes.
Yeah, because there's no actual shift in the EVM yet.
Okay, cool. Thanks.
So no problem. Okay, these next 2 lines, this, I better back up a bit. This is actually what's called an identity function. I don't know if you guys are familiar with it, but it's just a function that returns any value passed into it. It's a term from mathematics. I don't, people do use these, but it doesn't have a lot of functionality. But it's an easy example to give. So when this contract was deployed, it had a constructor parameter, so that. Oh, hold on a sec. Yes. I'm just trying to go over it again in my mind, because I just put this stuff together this morning. So all this does, these 2 lines, is it retrieves the parameter that was passed in from memory, that it was stored earlier, and it takes the value from storage at 0 and places it into memory at 0, because the return function can't use storage. It always looks for its return values in memory. So because we stored the return value at 0 in memory, this line just returns the location and the length of whatever was at 0. And then again, this is the equivalent of Solidity's whatever that default function is called. Anyway,
Fallback.
what's that?
Fallback?
Yes, the fallback. And if you don't actually assign a fallback, I believe Solidity adds this for you. It's just a jump tag 0. Tag 0 is an invalid location, so it gives you that invalid jump thing that comes up in Solidity a lot. It doesn't seem to make sense as an error message, but that's exactly what's happening in the EVM. It's actually jumping to an invalid location.
So I usually get an out of gas error when it throws, don't I? Or is that wrong?
I think that might have changed recently.
Yeah. I'm not sure.
Yeah, I get invalid jumps all the time. I never knew what they were.
Yeah, that's what they are. It's the EVM. The way Solidity implements its throw is by jumping to an invalid location, which causes the EVM to have an exception.
Cool.
So,
does that use all the gas
Yeah.
when it does that?
yes.
Okay.
Yeah, but I think they have implemented an invalid opcode now.
Yep.
So I think it used to be like jumping to an invalid location.
Mhm.
Maybe not anymore. But
Yeah,
I'm not really sure.
That's
If-
relatively recent, I think. This is actually a good way to start off talking about it. So I'll just go to my last slide. Oh,
Yeah.
I have a couple more things to say, then we can go into that.
Sure. Yeah. So I'll just type the things that we're talking about coming up
Sure.
in the chat, and then we'll address them later.
Yeah. Okay, this assembly format that we're looking at is a relatively new feature in Solidity. Core Ethereum developer Alex Berg-Sassi has done a mountain of work cleaning up and extending the EVM's assembler. Originally, it looked more like this, which is not too nice looking. But it is the equivalent of what we see in the new form of assembly. He's actually, with this format, he's actually working on adding function calls to assembly, which kind of is raising it more to a level of an actual language instead of just plain assembly, which doesn't have concepts like functions. To me, this type of thing is not much better than typing bytecode. So that's it for my whirlwind tour of Evm Assembly. I will stop sharing.
Oh, Daniel, did you show what that would have looked like in assembly, or I mean in Solidity beforehand, or?
No, but I do have that.
I'm just curious. Like, so I like what I gathered is like it would be basically something like simple storage, like or maybe even not that complex. Like it has one function. It's not the fallback function.
Yep. I'll find what I've got. Hold on a sec.
So Mike, this whole revert thing you're saying is the new opcode, but wouldn't that require a hard fork? I thought maybe
Metropolis.
No. So there probably was this unused opcode in the EVM, which Solidity just didn't care about before. Like they're probably just not using all the opcodes that are available. And they probably arbitrarily decided, okay, we can start using FE as an error opcode. That would be my guess.
okay.
No, I'm
I think it is supposed to be reserved for the revert, like when you're not gonna pay for the fees, right?
I went kind of deep on this one, and so currently Solidity compiles to a revert opcode, but which doesn't exist yet. So it's interesting to me because we're writing contracts in Solidity 4.0.4.11 that currently when you throw, you'll spend all the gas because they're compiling to revert, but that doesn't exist, so it's just treated as invalid. But after Metropolis, it will actually, that opcode will be recognized and will revert and you will get the unused gas refunded.
Oh, cool. Is that like when we'll be able to catch errors?
Yes, because that opcode will also return some. You can return some extra values.
Yep.
That's awesome. That's dope.
Yeah, I'll dig up a link on it.
Okay, so this here, I've just added a new slide, and it's not formatted properly, but you can see that the identity function is simply returning the input that was passed to it. So that's it. That's as long as it is in Solidity, and it ends up a fair bit longer in assembly. But this, when compiled with the Solidity compiler, produces like 3 or 4 times longer bytecode than doing it in pure assembly. So now I'll stop sharing my screen.
Thanks. I agree. The new assembler output is so much more helpful than the output it did before.
Oh yeah, I agree.
Yeah. So just so we don't let this die, I actually compiled 2 things for us to do in case anyone hadn't a better idea, hasn't got any better ideas. I've got opcodes for us to go through together.
Okay, good.
That could be cool. So a contract that is there, it is actually the multi-sig that Pancor is was using to hold the Ether. It had some modifications from the original Gnosis multi-sig. That's why it would be fun to locate those additional functions and maybe try to work them out without having to. Sorry, because we don't. And the other was just talking about the math library that Gnosis is using and how to implement a function in inline assembly to do the log base 2 of unsigned integer. So this is probably a little bit boring, and yeah, this could go into a conversation about standalone assembly, which I kind of tried to bring up on the channel the other day, but that is not yet implemented. So not sure which one you guys would prefer. I think going through the opcodes would be the most immediate one.
Yeah, one way to figure out how to do something in assembly is to write it in Solidity or in any other language, and then use the compiler to output assembly code. And then from there, you can see what it's doing and optimize that assembly code, and then plug that back into your Solidity code in an assembly block. So that way you get a good idea of what's going on. You don't have to write it from scratch, but you still get an optimized function. It's one way to do it anyway.
Let's look at some bytecode, Gonzalo.
I was also wondering if, like, maybe at the end you could talk about, like, is it a stack-based thing? Is it a register-based thing? You know, like.
Oh yeah. Yeah, the EVM itself is stack-based. So everything that's done is every opcode that takes values takes them from the stack. So they have to be pushed onto the stack beforehand. And there are, I think, there's push 1 to push 32 and everything in between. So you push 1 puts a byte on the stack, push 2 puts 2 bytes on the stack, and so on. There's also stack manipulation opcodes like swap and dupe and everything. But if we are sticking with the the new assembly type of output, we don't have to really worry that much about it, because when you specify a number, it automatically generates the push instruction to put that number on the stack. So it is a stack machine, but a lot of that is hidden, which I guess isn't that great, but it's hidden by the assembler itself, where, as I said, you put a number there and it will generate the instruction to push that length number.
I have a question.
Yep.
Hello, can you guys hear me?
Yeah, we
Sorry,
can.
I'm like outside. So you know how before you said they're changing the way the assembly is formatted to like support functions and stuff like that?
Yes.
Would that wouldn't be assembly language anymore, right? Because isn't assembly supposed to have a one-to-one mapping with like the binary?
Yes, exactly. That's
so like, are
absolutely
they
true.
developing so they're making an intermediate language to compile down to now, or?
Yeah, it will still compile directly to bytecode. There isn't going to be a step in between that and the binary that comes out of the compiler. But I think the idea is to make it easier for language developers to write the compiler to produce that assembly language. So there'll be a one-to-one mapping between a function in a high-level language and a function in this assembly language. There's good and bad things about with a higher level assembly and a lower level assembly, but I think the main function is so that all EVM languages compile down to this assembly language, and this assembly language is what is looked at and verified to be true and correct. So there's only one place anybody has to go to verify a contract it's in that assembly language.
Okay, got it. Thanks.
Yeah, no problem.
Maybe dive into the opcode stuff.
Sure. Do you have something?
Yeah.
Okay, good.
Sorry. I'll try and share my screen and maybe I'll send you guys the link first for Etherscan for the contract, so you guys can keep up. And let me share my screen. Maybe don't know if it's really necessary, but yeah. Okay, so
Yeah, please do.
yeah, let me. So let's. Okay. Not really easy to copy this stuff. Let me go all the way to the end. Okay. Yeah. So yeah, you guys. Yeah. So this is like the simply the already disassembled version of the bytecode. Like Etherscan does that for you. Like it turns the bytecode into opcodes, so it's easier for us to read. So do you want to guide us through this, Daniel? Maybe. So this, I can see that this 6040 M store. This is the free memory pointer, right?
I had a question first. Is there a way to see this in the new format?
Probably not.
Are we able to convert this to the new format?
You would have to have the source and compile it with Solidity's compiler with the -assembler option.
Oh, okay.
Yeah, I don't think those services actually do that type of disassembly. But this is exactly what it used to look like before Alex did the new type of assembly. This is what you got. So you had to figure it out.
That's right. Is it possible to, yeah, you probably won't be able to get it 100% correct without the source code, but you might be able to get an approximation.
Oh, yeah.
There's a tool that goes that way.
Yeah, because I think the thing with like with Solidity assembly, you still have variable names that you can work with, and maybe a few other carryovers from the original source.
Which makes that language move more towards a actual language as opposed to a one-to-one assembly equivalent or opcode equivalent. So I don't know how I feel about that.
Yeah, the way that I was getting at was, so if we know that mstore needs 2 arguments,
Yep.
right,
Oh, yeah.
then it definitely helps all the grouping together.
Yeah. I'm going to paste a link to a page I found a while back that helped me a fair bit when I was starting, that just lists the opcodes and their the hex numbers and the opcode name. I just lost the link. I'll be right back. Here it is.
Even extra new lines in this output might also help already. So if there was like a new line between line 3 and 4.
Yeah. So I don't have control over that, so Gonzalo will have to do that for us.
Yeah, sorry guys, I was distracted. Yeah, that Stack Exchange page is actually the only resource I know that has compiled the opcodes in a easy to read format. Maybe we could turn that into a read the docs thing in maybe we could make a Solidity assembly doc that doesn't suck.
Yeah,
because the current one is the information is just so scattered over the Solidity docs about assembly and the EVM quirks and stuff that it's crazy actually. But yeah, so I was just a little bit off. What are you guys asking for us to go through the opcodes now?
Yeah, and break them up by carriage returns in the different sections. Like the first 3 lines are one thing.
Yeah, and mstore is the instruction that consumes those 2 parameters, right? Do you want to do this yourself, Daniel? Maybe share your screen and guide us through, or if you just talk, I can do it myself.
Yeah. And as I've said before, I'm certainly not an expert on this stuff. So anybody jump in when you want to and correct me or correct anybody else or add information, whatever. So the first 3 lines are fairly straightforward, but not if you aren't familiar with the stack machine and the opcodes that EVM has. So mstore stores a value at a given memory location. So the first number that's pushed is the value, and the second number that's pushed is the memory location. And mstore takes those 2 things and stores 60 at 40. And as Gonzalo mentioned,
sorry, guys.
Yep, as Gonzalo mentioned, that at 60 is the free memory pointer. So your code is in another area, so you have a completely empty memory space in which to put values. So this takes 60 and puts it at 40 because the next byte or the next word after 40 is 60. So when somebody goes to look for the next free memory location, it goes to location 40 and gets the value there. It starts at 60, and as you use up memory, it goes up. So, and the reason that the value is stored at 40 is because the first 2 words, 0 and 20, are used as scratch space by the Solidity compiler. So whenever it doesn't say a SHA-3 or something, it'll store the values there and then point SHA-3 at that location. So the first 2 words are sort of up for grabs by anybody, but don't expect to put something there and have it stay there.
Yeah, and like sometimes Solidity needs more than the scratch space it reserves by nature, and then it just uses the first free memory space it finds from the pointer. But so be careful about that, because you don't know when Solidity does that, and if you are expecting, like if you are expecting that the free memory pointer is null, it may not be. So Solidity may have used that if it was doing some strange operations. Probably not with unsigned integers, but with some crazy stuff that needs more scratch.
But you can cooperate with the Solidity compiler or whatever, the EVM executing this. What you can do is whenever you do use free memory, take that pointer, put the things in that location and update that pointer to just past the length of what you've just put, because Solidity will go there to get the pointer as well. So your stuff will still be safe as long as you manage the pointer.
Yeah, sure.
What line are we talking about right now?
Pardon?
Not a line, actually. We were just talking about the Solidity's inner working, because we're still here, actually.
Yeah, we're at the first.
This led to the space thing, because the free memory pointer is in Solidity's first few bytes reserved space for either scratch space or the free memory pointer. And that led to a conversation about Solidity's memory management. And I was saying that sometimes Solidity needs more than the scratch space it has reserved in the beginning of memory. And so it overflows to the free memory pointer location, and it just uses that as scratch space, and it doesn't null out the memory it has used. So if you're accessing memory there directly, with inline assembly and expecting for the free memory pointer to be always zeroed out, it may not be. That was the thing.
Yeah.
Okay, I think that makes sense.
The free memory pointer is 0x40.
Yeah, that's where the pointer is stored.
Yeah, and so what I heard Daniel say was, you can mess around with the free memory as long as you make sure yourself to update 0x40.
Exactly.
So it can go ahead and continue doing its own stuff.
Yep, that's exactly it.
Yeah, so I think I can do this next block.
Sure.
So call data size, we're checking if the transaction actually has data with a length bigger than 0, because you get the size of your call data of the transaction. Call data is actually a memory space to write, Daniel, because you've got your storage, your memory, and you've got call data that is a completely separate memory location. It can't be rewritten. It is static from the moment the transaction is made. And the information that is there can only be read, not written. So you get call data size, and if it is 0, you push 2 bytes to the stack and you jump to that location. And I'm guessing this location is the fallback function, because if you don't send any data, you're gonna hit the fallback function of the contract and you're gonna jump to that location. So this should be the fallback function, right?
Yes.
Cool.
Because even if you call a function and it has no data, there is still call data, because the ID of the function is still necessary. So if call data size really is 0, then no function was even asked for and no data was passed in, so it does the fallback function. So I believe you're right, Gonzalo.
Right, yeah. So the first 4 bytes of call data are always the function signature.
Yep.
Then that's the way they do function management.
Yep.
Cool. Okay, so let's not jump into the functions already. Let's. Someone want to do this?
Let me add something quickly here.
Yeah.
Sure.
Just if call data 0, that's for everyone else who might be less familiar. That's the case when you send a transaction and all it needs is 21,000 gas. Once there's some call data, then you need more than 21,000 gas.
Okay, yeah. So does anyone want to do this one, or should I? I think I can as well.
Mm-hmm. Sure.
So we're pushing 4 bytes all one out. So this is the max value of 4 bytes. That is actually a mask, right? This is actually a mask for the call data that you're retrieving here. So the thing is, you're gonna retrieve the whole call data that the transaction has, because it has some, otherwise you would have jumped here, here. And then you just mask this to get just the 4 first bytes, right, of the call data. And you're actually gonna compare those first 4 bytes of the call data against function signatures all throughout the rest of this initial code block. This is a bigger than a code block. So these are all of it are just function signatures and function locations in memory. And if those 4 first bytes of the call data that you just loaded are equal to any of the function signatures, you jump to location.
So this is in effect a switch statement or case statement. So it's just looking at the value, comparing it to every function signature it knows, and if it matches, it jumps to that function, which is, say, on line 26, push to 019B, and then jump. That's the location that matches that function signature. So that's a whole pile of just trying to figure out which function that was asked for.
Yeah, also, I didn't mention, but this division here is just for, like, you mask the lower end bytes, and you just divide to get the high order bytes of your call data load down to the end, so you can mask them on the low end of the 32 bytes. Is that right?
Yep.
Cool.
What's the push 00 after that? Push 1 0x00.
Good question. Not really sure.
It's loading the call data at 0. So it's grabbing the first 32 bytes of call data. You can index into call data any way you like, but taking it from 0 includes the function signature as the very first 4 bytes, which is what you're masking off in the next lines. So all it's doing is getting the first 32 bytes of call data.
Okay, so call data load takes one argument on line 12, and then since it's this stack-based thing, then when you get down to div on line 14, it operates on lines 10 and 11?
It operates on what has been pushed to the stack in the meantime. So, So when you push 100 call data load will actually put the number that it retrieves onto the stack. So everything has to be on the stack when it's being operated on.
This is probably a good link to follow what we're talking about, because it has the assembly functions and the parameters that they can take. So call data load takes 32 bytes per meter. That is a position from where it is.
Yep.
Kind of the race rate. Yeah. So going on. There's a whole lot of this. I can try to just. Okay. Yeah. This was a little bit. Yeah. One last. Oh, sorry. Yeah. Okay. So up to here, it's function signatures and function locations. We can just start here then. So after the last functions like switch case thing, we actually have static jumps. So not really getting this static jump here. Why would we have a jump and then a push and then another jump? Really following.
Those aren't jumps. Those are jump destinations. So every jump in the EVM has to have a jump destination. If it doesn't have a jump destination, it throws an error, like the one we see all the time. Jump dest is not represented by an opcode or a binary number or anything like that. It's just the place. It's marking a place that can be.
Okay, cool. Sure. Yeah, got it. Okay.
No, but I didn't. Can you finish that, Daniel?
Oh, sure. So the EVM has to have a marked destination to jump to, marked by jump dest. If it doesn't have that, if you jump to a location that isn't a jump destination, it will throw.
Yeah. Okay. So like on line 145, 0x016a.
Yep.
That's the destination that we're going to go to, and we'll see if there's something there or not.
Not really. No. Jump dest is only for reference. It only is somewhere you can get to. Jump dest doesn't have any operation. It doesn't do anything. It's just a marker. So the numbers at the top, say line 128. Whoop.
I was just jumping to what you were saying. So if you're pushing values to jump calls, right? Jump opcodes. Yep. And you can only jump to these destinations if you have a jump dest there. Is that it?
Yep, that's exactly it. And if you're off by a byte or you're off the end of your actual byte code, it'll throw.
Cool. Exactly. So this is a marker.
Yep.
Okay, so that it's not easy to know what actually jumps to that point right now because we don't know what location it's at.
Yeah, exactly.
But if we counted the bytes until we got to that one, then we would know what jumps there.
Yep.
Cool.
So setting your jumps, the location or the destinations of your jumps correctly depends on the ordering of the opcodes or of the assembly code.
Not necessarily on the order, because say line 128 again, that's the location it's going to jump to. If that location isn't a jump dest, then it throws. So each of these,
so like on line 143, why is that jump dest there? I mean, I guess the compiler knows about it, but it would be impossible for a human to reason about it.
Yes, something above that targeted that location, just like on, say, 128 push to 05BB. At 05BB, if you looked in the code, there would be a jump dest.
Okay, that's very interesting. Cool.
Yeah.
I feel like it'd be, I'm sure there's some way to do this, but to actually, if each line had its location number.
Oh yeah. Yeah, so you probably wanted GBB or either Pro for the EVM.
But the thing is, any jump destination can be jumped to by any bit of code. So there's not only one thing that can jump to a jump destination, so there's no way you can say it came from there.
Yeah. So that's usually
Mike's question.
What's that?
To touch on Mike's question, since we did temporarily put in all these new lines, assuming that there were valid opcodes in there, then we would have messed up all the jumps. So we are not we wouldn't be allowed to the jump destination.
Yeah, so I want to say that if you think about traditional architecture and I disassembled a lot of stuff and I used to put knobs there were no opcodes. That was the meaning of them. There were 90 in Intel 32 bits. Like I used to put them just for reference, for my own reference, when reverse engineering something, and I could put them all the place, and the program would still run. If that is your question, Joseph, I think if you put an op here, like if you put a and just an opcode that does anything, you would measure jump destinations and nothing would run.
Yeah, and don't forget, this is just a text representation of the actual bytecode, so spaces don't really matter in this case. They aren't specific, like there's no line 05BB in this file. It's more where the program counter goes in when the thing is being executed. This here, with spaces or not, doesn't matter. Like if you were writing this yourself, you would probably put lots of spaces in and comments and things. But since this was produced by a debugger, there's none of that.
Okay, let us continue then.
Sure.
So this is the first jump destination that we get. So I imagine this is the fallback function, maybe, not sure. Like if I would be following any kind of thought process as a human, like I'd probably make this the fallback function. Not really sure what the compiler does though. So here we push some value, and then we have another jump destination. So this is probably just made to prevent pushing this into the stack. We actually get the call value at memory 0. Right, so call value, this is not called data load. Call value is, chime in, Daniel.
Call value
is just message.value.
Yeah, it's the value of what.
So you're not comparing to 0.
No.
You're comparing to 0 when you're doing the GT at the next line.
Yep.
Yeah. So
call value is would be non-zero if you passed any ether to the function. And that's what's checked if you don't have, if your function is non-payable, it checks call value to make sure it's empty.
Sure. Yeah. So this GT opcode is just the greater than comparator in the EVM, in the virtual machine, which would output 0 when comparing the call value, and the byte that was pushed would equate to 0 and then would jump here because the flag would be set if it was greater than, right? And it would jump to this location.
One slight clarification there. GT will put a binary, a Boolean on the stack. Is 0 will invert that Boolean.
Oh, cool. Oh, really?
Yep.
Didn't know that.
Yeah, the Solidity compiler does that all over the place. It's not easy for us to read, but hey, the robot knows.
Right. So this is actually okay. I could start commenting on this. So this is actually actually the payable modifier, right?
Yes.
In Solidity.
Yep. And let's see. Push 0. If call value is greater than 0, it means that value is passed in, but then it inverts it, and jump I is jump if. Jump if non-zero, I'm not sure. Jump if 0. So
yeah, if 0, yeah.
Yep. So
why not just compare it? Why not just call value and then is 0? Why the extra step?
Because it is checking greater than, so that you're inverting the comparison. You're not checking if it is 0. You're checking if it is greater than.
And then is 0 inverts the flag, I believe, because jump I needs, I can't remember which, but it only jumps if a Boolean is either true or false. I'm not sure which it is on the stack. So I'm sure is0 puts it to the state that it needs to be to do the proper comparison and jump. So in effect, this section will just look to see if there's a value, in-call value, and if there is, it'll jump to whatever 0167 is, which is probably it's probably the fallback function or a way to get out of this.
Yeah, so one thing that usually helps me when doing this is actually doing going and writing the actual solidity function, assembly function myself. So jump I, this would have the like this, right? And then is 0 GT message dot value 0, right?
Okay.
Something like this.
Yep.
Yeah, so this kind of helps me to visualize stuff. So
Yeah.
we're doing greater than on message value and 0, then we're checking if it is 0. I don't know if this I may be completely misleading you.
No, that's where it inverts the Boolean that was retrieved by the GT.
Yeah, so I'm not really sure if that exists in Solidity assembly grammar, but yeah, so that
sure
maybe it does. Yeah, it does. So if is0 checks if x equals to 0, and then it outputs 1 to the stack. Yeah, so it's cool. It does.
Yep.
And this is the payable. Yeah, cool. We got one assembly function written, and we attribute it to the payable modifier. So this is what the compiler appends to every bit of every function that has the payable modifier. And this is cool.
It's actually the exact inverse. When you specify payable, it doesn't check call value. It just goes on because it expects a value in call value. If you don't specify payable, it does this check.
Oh, yeah.
Sure you didn't pass anything in.
Cool,
So,
cool. Yeah, sure.
When you say payable, it doesn't affect the function that you put payable on. It actually removes code when you use payable. So every other function that is not payable has extra code added to it. So that's one thing to keep in mind if you're trying to optimize.
And just to Zach's question, yeah, we're looking at unoptimized code. So the Solidity optimizer, it might just remove that GT0, and it might just be able to do is0 call value.
Yeah, exactly. As I've mentioned before, the almost any compiler is pretty inefficient. So, but normally it doesn't really matter that much. But with Solidity, or with the EVM anyway, with gas costing as much as it does matter if things are wasteful, which is almost why we're here.
That's interesting. That's interesting if that particular part is being wasteful, because it's sort of something they hard coded into the compiler.
Yep.
Like you're saying, it like adds extra code if you don't put payable. So it's like they sort of, and I remember when they added that, like there was like problems with people accidentally sending ether places.
Mm-hmm. Yep.
Yeah.
So, but of course they only added it because people were sending money into functions that didn't need it and they were losing it.
Yeah, so by now, stack slot number 3 is stack slot number 1 is this one, right? Because we can't forget about things that were pushed earlier and that weren't used. So this is probably the way that the compiler is working, because we were sent here. We may have sent here, And then we started doing some other stuff, but like if we were sent here, we still have this in the stack. So this may be important. Let's just make a note of that.
Yep, exactly.
Cool.
Yeah, when I started learning this, the EVM bytecode, I would actually annotate every line with the stack at that point, so I could keep track of what's there and what has been taken off. So it was just in comments, and it's just helpful to know at every point what's on the stack.
Yeah. That's the thing that I was talking about the other day, that you get, like, if you start reverse engineering, there's like a few tricks that you start using just because you need, right? Because otherwise you lose track of things, and that's usually the way debuggers work in traditional architectures. They do all these pesky things for you, but we have to do it, or maybe we will build the debugger for the EVM.
Yeah. So
I don't know if you guys want to keep going or if I should shut up, stop, whatever.
I just have one shameless plug. The Solidity compiler does produce really inefficient bytecode. The LLL compiler produces extremely tight and efficient bytecode by default. So an easy way to get a more efficient bytecode is to write it in LLL. Not that I have a mission or anything.
No, we get that was completely harmless. Yeah.
The funny thing is, I actually did do a test, and the assembly output from a very short LLL contract looked like it was written by hand in assembler. And it's not an exaggeration, so just something to keep in mind.
Hey, I have a question.
Sure.
That's like maybe connected to what we were talking about. I thought of it when we were talking about how Solidity lays out memory in the free memory pointer. I'm thinking about how when stuff is getting put in storage, it's laid out like one after the other. And like, how does Solidity internally know where to put new variables in storage? Like, does it also maintain a pointer to like the next free storage location? Is there something like that going on?
Not at all, no, actually.
No.
Sorry, storage.
How does it know?
Storage is entirely key value based. So it's a very sparse structure that only has data associated with a key. So you can think of it as a hash, but you don't need to know where the next one is, because first of all, the storage space is pretty well infinite in its locations. And secondly, you only can get a value from storage if you've put it there in the first place and know where it is. So it doesn't add on to the end in any way at all. It just uses keys to get value out or put values in.
Right. So when you have a mapping, there's this. Let me find this snippet.
Yep.
I'm going to put it in the chat.
I thought you said trash.
Oh, well.
Put it in the trash.
This is how if you have like a balances mapping, this is the like location that balance is stored in storage, right? So the position number, I've observed that it changes from contract to contract. And it's usually an int, like it'll be 1, 2, 3.
Oh, I see what you mean. Yes, in that case, what is happening is it's sort of like a base location plus an offset. So in Solidity, when you do a structure, that structure has a base storage location. When you want to access pieces of that structure, it adds the offset to the base number to get the value you're looking for.
I see. So sort of like the value of what's at the location that is this key is an array, and position is the index in that array. Is that sort of?
Sure.
Yeah, sort of.
Yeah.
Yep.
And the references in assembly, in Solidity assembly, to storage vars are not made as you would reference memory variable. So if you want to access x that is an unsigned integer in storage, stored in storage, so you'd have this pointer to its slot in storage, and then you'd have another one for its offset, because storage may be tightly packed. So you've got a 32 byte slot that have this pointer representation in assembly, and then you inside that slot you have a certain offset where your variable is. Of course, if x is if we have x like this, so in the storage, I guess you'd have x like right in the beginning of your contract. Like if you have contract whatever, like contract x stuff, like if you have that, and like this right after, it would be x slot, it would be 0, and then you'd have x offset also 0 because it occupies the whole 30 bytes. But maybe if you had it like this, and then let's make it a little bit different. So let's make it like this. So now x slot is also 0, but your offset is now like 1, right?
1. Yep. That's what I was going to mention, actually, that memory is byte addressable, storage is not. Storage is word addressable, 32 byte word, or 256 bits. So it only jumps 32 bytes at a time. So you can't say, so in other words, storage spot 0 is 0, storage spot 1 is 1, kind of obvious. But in memory, storage spot 0 is 0, and 32 byte storage spot after that is 32, not 1. So you're going by bytes with memory and words with storage.
So basically you're saying that the code right there would be the same if he had done uint 256 or whatever? It's taking up a whole slot, like a whole word.
Yes.
Either way.
Yes, and that's why sometimes it's inefficient to use smaller than 32 bytes, because it has to do some gymnastics to actually address it as a byte.
Yeah, it does. Like it masks. If you use smaller than 32, it always has to mask the 32 bytes it addresses.
Yep.
So you're putting like 3 or more or 4 more instructions in between.
Okay, and I've heard if you use a struct, then it can actually kind of compact multiple variables into one.
Yes, but at the same time, you still cannot address it as bytes. You have to read the 32 bytes in and unpack it yourself.
Okay, so you'd have to do that masking thing in order to deal with the variable.
Exactly. Sarah, did that answer your question about storage locations?
I think it did, yeah. I still have maybe half a question remaining, which is that, so the offset position, Solidity does track that.
Yes, and it's according to the size of the data you're putting in there. Actually, no, I'm sorry. It's word addressable, so everything is 32 bytes apart, or 1 word apart. So offset 1 is Gonzalo's put there, and then offset 2.
Yeah, that makes sense. Is there a name for what Solidity calls the X offset here? Like, does it have a proper term for it?
It's hidden by Solidity. EVM bytecode is entirely flat. There are no structures whatsoever. So when you use a structure in Solidity, it has to be represented somehow in bytecode flat. So they've used the idea of a base location plus an offset. So offsets are in storage are like 1, 2, 3, 4. So if you had a structure with 4 UINT 256s with different names, they would be at location at offset 0, 1, 2, and 3 from the base address of that structure.
Okay, cool note here.
I think I understand better. Thank you.
Okay, good.
Gonzalo, so these examples that you're doing, right? Yeah, this seems more like if this data is inside a struct, that's what you would get. Otherwise, you know, like let's say look at contract X1. Why would that, you know, unless Solidity is already doing optimization, Y and X would be in 2 different storage slots probably, won't they?
Yeah, but Solidity does that not only in structs, but also in the storage itself.
Oh, okay. So it already knows that, it already knows how to pack them without you having to use a struct. Is that what you're saying?
Yeah.
Okay. Maybe in the old Solidity, you had to use a struct to give it the hint. Okay.
Yeah, so that's what I've read from the docs, but like it may be untrue. So please take everything I say with a grain of salt. There's a thing that I would like to note. However, like this, in this scenario, like you've got this, you've got this, and then you've got this. So like Solidity doesn't know how to pack things smart. Like the compiler isn't that smart, so it doesn't group Z and X automatically. It just reserves a whole 32-byte word for X, and then as Y needs a whole one, it reserves another for Y, and then another for Z. So it's not smart.
It gets even more interesting when you want to have a multi-dimensional array and represent that flat. So there's a couple of ways to do it, I think. One would be to have the base location have only the base locations of single arrays or single dimensional arrays. And then you go there, you get the base level address of the array, and then you go to the location and get the base address of the second dimension and work from there. But you have to know, I mean, the Solidity compiler does it itself, but you would have to know exactly the layout you want to do. So it's all manual, entirely manual.
Cool.
Yeah. A future one of these that would be interesting is talking about the bytes data type and the string data type, which is what you're getting at there.
Yep, which don't exist in EVM either. So yeah, that sounds good. I could talk about this all day.
Yeah, I guess me too. Do we want to keep going, or I just don't want to push people into?
Oh, we have 10 people left, so they would have left if they were bored. I think, maybe not.
Yeah, cool. So I'll just keep going.
Sure.
I'm having a lot of fun.
Pardon?
I'm having a lot of fun.
Oh, cool.
Okay, so let's keep going. So we have this on our stack still. So this is probably a jump location that we're going to use somehow later.
Yep.
Sorry, I did have a question about that stack location, Gonzalo, because if we did come through the jump dest in 146, right, then
go back up a little bit more.
One doesn't necessarily have to be that.
Yeah, if it arrived at this location at line 146, that would not be on the stack, no. But if it arrived at 143, the first thing it would do is put it on the stack.
Yeah, got it. So right now we're assuming that we went through line
yeah, exactly. Yep. So I'm assuming we arrived here, and this is just some assumption of my own. I'm not even remotely sure of this, but I'd say this is the fallback function, the fallback function, but I'm not really sure. So I'm just gonna note it here.
Or is the fallback function at 016A, and when you jump there, it jumps to an invalid location?
Oh. There you have it. Okay, let's keep going and try to figure out whatever the heck is going on. Also, by the way, just a quick note. So I just chose this contract because the Gnosis multi-sig, I just put it in the 4-byte directory web app, and all of these function signatures are known except for this one. So I don't know which function this is. This is the thing that we wanna decipher. So yeah.
Okay.
Which, as I'm seeing here, says 016C. So this is like 2 bytes below 16A.
Yeah.
Right.
Well, depends how you look at it. To me, it's 2 bytes above.
yeah. Okay. And yeah, so yeah, not sure what to do with this information, but let's keep going.
Yeah.
Do you understand? Please save me here.
What's that?
Save me whenever you can.
Oh, well, line 201 is very interesting because it goes back to what we talked about earlier. You want to take it?
Line 201. Yeah. Okay. So this is pushing this byte for it that is into the stack. This dub1 just exchanges the first slot in stack with the second one, right?
Almost. Nope, it duplicates.
Oh, duplicate.
Yep.
Oh, it duplicates. Okay.
There is a swap as well. But
oh yeah, that swap. Sure. Yeah. I don't know what I was saying. Yeah. Sure. So this actually duplicates the byte, and then we do we'll load memory from this location.
What does it give you?
It gives us the memory pointer.
Yes.
And then we do okay. Let's do let's do that again. So by now we have message.value, and then we did an mload with, so we did that.
Mm-hmm.
Okay. Do duplicates have assembly an assembly instruction for those? Yeah, they have, right?
Yep. And there's dupe 1 to dupe 16, I believe. So it doesn't duplicate 16 stack items, it duplicates the 16th stack item or the 12th stack item on the top of puts it on the top of the stack.
Yeah, right. So what this is doing, it is actually making mload takes how many parameters? 2, right?
Yes. Yep.
So what this is basically doing, if we're gonna unfold that, this is gonna give us something like this, right?
Yeah, I think so.
Okay, I don't know how to write this. Let's keep it like that, just so we don't get this doesn't get any more confusing. And then we duplicate this to the yeah. So this is it, right? No.
Don't forget, dupe 2 duplicates the second stack item. It doesn't duplicate 2 stack items.
Sure. Yeah. So this is only 1 parameter, and that's it. This is getting really strange to write it like this. Yeah, we should just go over the code. So and then we duplicate the second stack value, and we
What do
store
we-
that.
Why don't you mark what's on the stack for each line? So at
Okay,
line 2
yeah,
and 5,
cool.
let's assume there's nothing on the stack at the moment.
Mhm.
Even though there is, we know, but it doesn't matter.
Yeah, so how would you represent the stack here? Let's
I would just put, when I was doing it, I just normally put the numbers that are on there. So 40.
Okay,
And
so we have,
the next line would have 2 OX40s.
like this?
Yeah.
Cool.
And
And then mload consumes those
consume,
two.
no, it consumes 140 and replaces it on the stack with with what's at location 40. So that would be
Okay.
60 in this case. So mload takes the number on the stack and loads from that memory location. And then it goes back on the stack automatically. So on the stack after that,
I have,
depends on which way you're looking at the stack. To me,
okay, rightmost is top.
yeah. Because then you can add them on the end, and that's the
Sure.
bottom or top of the stack, or the left or right of the stack, depending on how you look at it. So yeah, after the mload, there'll be OX40, OX60, and then call value just pushes the call value, so it'd be OX40, OX60, and whatever call value returns. I don't know what it is. We don't know.
Yeah, so call value pushes to the top of the stack, right?
Yep. So 40, 60, then call value. Yeah.
Okay.
So do
And we duplicate the second
Mhm.
the second. So this is the second slot in stack, or yeah, no, this
Nope.
is
Call value is on the stack, right? So
yeah,
60 would
yeah.
be the
So
second
60,
thing.
yeah.
Yep.
Is there a certain number of bytes that call value has to be, or
It's probably 32 bytes.
okay?
I'm not
Yeah,
certain
but
of that.
these are all
Yeah.
all 32 bytes, right? So
Yep.
I would, if this was to be done correctly, I should be
Yes,
just
yes.
padding this with zeros.
Yep.
Okay, cool. Yeah, I didn't know that.
Okay. So now mstore will take the top 2 items and store.
This, so let me try to guess it. So
Yep.
it would store the second item on the first one at this location.
Yep.
Okay,
So
yeah.
then-
So this doesn't mess with the stack, or does it? Does it
Oh,
consume
it
the?
does. mstore will take the top 2 items off the stack.
Cool. Okay. Makes sense.
Yep.
And then you can just note that at location 60, the call value is now stored.
Yep. And
Yeah.
but the memory pointer has not been updated yet. So that'll probably happen in the next few lines. I'm not sure. Because the memory pointer still points at 60, right? And we just put something at 60.
Wait, Gonzalo, the note you're doing is for the next line, right? With the mstore.
Oh, yeah. Sorry about that.
Just don't let it happen again.
Okay, yeah. I guess after this, we should probably continue next because now we have 8. But
Yeah, we should stop. Is that what you're saying?
maybe seems
Yeah,
like we have 8
sure.
people now from 10.
Sure.
Yeah,
Sure.
the next,
Okay. Yeah.
the next set of lines are going to be really confusing anyway. I don't even know what to
So-
do yet.
So we now have the mload, the put the whatever is that.
Yeah, so swap 1, it was 40-60, now it's 60-40. So mload will take 60 and, or wait a minute. Let's see, mload will, oh, okay, it's just loading from 40. Mload just takes one parameter and it's loading the memory, what's at location 40, which is currently 60.
Oh, yeah. Oh, right. Yeah.
60, yeah.
Yep.
Did we ever update the memory pointer though?
Not yet.
Okay.
So let's say we'll end here. We'll end here and leave it for next time. No, sorry.
Yep. And then again.
Yeah, so.
Away, O2. And then it does some weird math. Very fancy.
Oh.
Yes, that's right.
Okay.
So exp, forget how many. Oh, it takes a base and a exponent and goes the base to the exponent and then puts the result in the stack.
In which order? So it's
2 to the A.
2 to the A0. Okay, so we now have 60.
So it's 2 to the 10th.
2 to the 10th. So how? So it's that in X is how much? So.
But wait, A0 and 0A. 10 is 0A, but A0 is not 10, right?
Oh, you're right. Sorry about that. Yes. That might actually be 224. I'm not sure. Hold on. Got my fancy calculator. Not a real one, of course. View.
Is that even going to fit in one?
A0 is 160 in decimal.
Okay.
So yeah, we're doing something with an address here. Looks like so 2 to the 160.
Yeah. A0 is what in decimal?
160.
160. Yeah. Okay.
2 to the 160 is now on this.
This is 160 in X. Yeah. So let me copy that. Let's try to see if I got it right. Is this it? Did I get it right? Is everyone check? Is anyone checking? No. I think so. So yeah, I think I got it right. So that's it. That's what's in the stack now. And then this, I guess this subtracts, right? And in which order does it subtract? Let me.
On the exp line, I think you have the same stack as on line 215.
So,
I think that should be up there, up on 216. I think.
Oh, okay, yeah, sure. Like this, you're saying?
Yeah.
Yeah, and then this just subtracts the first one, the second one from the first one, right?
Yeah, I think so.
So yeah, let me fire up my calculator again. Yeah, -1. Yeah, cool.
All these modern conveniences.
Yeah, so this is it.
Yep.
Oh yeah, it wasn't that hard to do.
And
then color
is
cool.
message sender.
So let me try to guess this one. So 1, 2, 3, 4. This is not a. Yeah. Help me then.
Yeah.
Oh, did I get it wrong?
Maybe.
Joseph?
Is the exponentiation right? Shouldn't it just be like shouldn't it have just shifted the number, or is that totally?
Yeah, that's what it's usually used for.
Okay, so I would think if
it's shifting.
it would just have like 40 zeros, I think. There'd be like something,
0,
number,
X1,
and then
and zeros.
maybe like a 2
Yeah.
and 40 zeros or something.
Cool.
Or a 1 and 40 zeros.
Okay, so we actually have this much
Yeah.
F's. Yeah, right?
Yep. Yeah, all of the F's. Yep. Looks like it.
Yeah.
Yeah, so this is not going to work. How many is that?
It's hard to say.
Just put a few. We'll get the idea.
What you want is that the 0x1000 is all F's instead of zeros.
Yeah.
That looks good. Without the zeros, of course.
Yeah, sure. Okay. Okay, and
all caller does is put the message sender on the stack, the address.
oh, is it? Ah, cool. Didn't know that.
Okay, so it's gonna check if message sender is equal to something. Right.
No, then it ends it with the FFF line and does other stuff that we're going to get to next.
Yeah, so this, I'll guess that this is actually 20 bytes, and right, and it is just putting a mask on 32 bytes to get an address.
Yep, you got it.
Cool. Yeah. So
big reveal.
Awesome, guys.
Fantastic. So I hope this was helpful to people. Yeah.
This was so much fun.
I agree.
This was awesome. We just got deep in there. That was really cool.
Excellent. So we'll have to do another one for sure. So.
Yeah.
I had my camera on. I was probably doing some funny faces.
Yeah, we didn't want to say anything, but.
Do you want me to post this somewhere? The whole thing I have been writing. Yeah, so I will post it in the roundtable channels, just so if someone wants to pick this up like on the next session, anyone can. Cool.
Excellent.
Awesome. And I'd love to see the slides too, Daniel.
Oh, sure. It's a Mac Keynote file, but I can export it as something else, I think.
It's okay. I think I probably have that program.
Okay. Well, if you have an OS 10 machine, then you have Keynote.
Yeah.
Okay. Yeah, I'll send them to you. I'll do it in Slack. I'll do it in that roundtable Slack channel thing.
Okay, great, guys. Thank you so much.
No problem.
Thank you so much, guys.
Thank you.
Thanks, everyone.
See ya.
Thank you.
Thank you. See ya.
Thanks, everyone.
Bye-bye.